So thank you very much. I'm from industry, so I will give you the outline of an average industrial talk. Industrial talk usually starts from a little bit advertisement of our company, of our products. The next step, I should describe the research, what we are doing in our group. Next, a little bit more advertisement, thanks, and the usual we are hiring part. So we are hiring. So now, but to break the pattern, I will start from a funny story and not from the usual thing. So it is a well-known story in computer vision that in 1966, Marvin Minsky, one of the founding fathers of artificial intelligence, asked one of his undergraduate students to link the camera to computer and to write the program which describes what it sees. Now, Marvin Minsky asked him to do this in 2 months during the summer. So generally speaking, to solve computer vision in 2 months, not a problem. Now, today we understand that it took a little bit more than 2 months, but we have a date, 1966, we in the 2016, so happy 50th birthday to computer vision and to all of us who are dealing with it. Now, and at the same days in 60s, in 1968, one of the Marvin Minsky PhD students, Adolfo Guzman, wrote the first paper, probably one of the first papers on the scene understanding. So it's exactly the same period, 1968. And what else happened in 1968? 2 young guys, Gordon Moore and Robert Noyce, 2 young PhDs, physics, they left their company, they left their job in Fairchild Semiconductors to found a small technological startup, Intel. So here's the connection between Intel and scene understanding going back to 1968. So here's the advertisement part, 48 years, fast forward, 48 years, we are in 2016. We in Intel producing so-called RealSense technology. RealSense technology including the hardware, the 3D cameras, and some of the cameras are related to Technion. One of the cameras was invented here by Ronnie Kimmel and Alex and Michael Bronstein. And we're also doing multiple middlewares, the 3D capture and the face recognition and the gesture recognition, which I, with my colleagues, did previously. Now, our cameras are installed in multiple OEM devices, tablets, laptops, all-in-one computers, even mobile phones. But our face in the future, so we do understand that the future of computer vision in general and the future of many of our 3D technology is in the fields of robotics and virtual and augmented reality. And in the fields of robotics and virtual augmented reality, there is one common problem which is still unsolved and of very high importance. It's a scene understanding. And when I'm saying scene understanding, I don't mean to recognize that this is the lecture room or living room, but actually to create the fully blown scene understanding. So so this is a description of the problem. We have an RGB feed from RGB camera, and together with a feed from the depth camera, this is the input into scene understanding system. And what we want to create, it's a blueprint. It's actually a virtual blueprint of the room we are in, and to recognize all possible objects in the room, and not only what are the objects, but their 3-dimensional structure, their boundaries, how where the robot or the person who is scanning can move, the movable paths, and maybe even, on the next stage, depends on the application, object-to-object relationships, robot-to-object relationships, and stuff like this. Okay, so this is the problem which was defined to us. We are engineers, so we are starting to work, and we engineers, we like to create systems, pipelines. So we created a system, very, very simple prototype. The input, RGB and depth feed. On the next stage, we create a so-called 3D. So it's, generally speaking, Kinect Fusion algorithm. We create the volumetric representation of the room. Next, we did some very, very rough segmentation. It's a prototype, not something complicated, mostly plane fittings. Using this segmentation, we wrote few heuristics, combined planes into multiple proposals to create object candidates. Object recognition, nowadays, it's an easy task. We can use, project the 3D bounding box into the RGB image, run your favorite CNN, and we will have objects in no time. And finally, we did some very, very rough registration, prototype, nothing more complicated than a simple ICP from a handful of models that we used to for our prototype. So here how it's worked. Now it's an example. RGB scan, RGB feed, in the middle depths from the Kinect Fusion. And on the right-hand side, you see, as soon as we have enough data, we can do the segmentation and bounding box. And as soon as we have a bounding box and recognize that this is a chair, we can try to do some ICP. Now, luckily for us, we had only a handful of the models, so it will be difficult to mistake the table and a chair. So it works very well. Now, it's a very, very simple system, and it's a long movie. But, we can increase complexity of the system as we want. For example, this is one of the latest paper from Princeton group. I don't see Tom here, but this is from Princeton group. Instead of the very simple segmentation and heuristical bounding boxes, they used the same volumetric data which we used, and they produced the deep neural network on the volumetric data and the so-called deep proposals. And then instead of the simple projection on RGB, they used projection on RGB together with volumetric data, and produced a very, very good object recognition. But we felt that something is not right. So it's not like a natural scene understanding works. So I have no idea how natural, so this is why I put quotation marks, how natural scene understanding works. And yesterday I spent almost 1 hour trying to find some movie with toddlers trying to understand the scene, but I failed. So here's another movie. So this is how our scene understanding works. We immediately understand what we see. Now, but we continuing to incrementally to add information to what we see. And sometimes the information can be, contradictory, but at least it will add some more knowledge in the system. And then we can interact with the system. So we can understand what is wrong, or we can move into the direction or move the object to understand what we don't understand, or which information is lacking in this picture. So we wanted to make a system which is more naturally. The naturally, once again, for us was it's instant, it's working in real time immediately, it's incremental, and it's interactive. But we already have one sub-module in our system, which is real-time, incremental, and interactive. It's so-called depth fusion or Kinect Fusion. We don't like to advertise our competitors. Now, so how Kinect Fusion it works? We have the volumetric model of the world. We receive the new depth image, and we're trying to align the new depth image with the camera position, to create the camera position from the alignment of the depth new image and the module. And as soon as we have it, we can update the model with the new arriving data. So this is how Kinect Fusion works. So you see, you immediately have a image, the module, and at each movement we add more and more information. And if there is some holes in the information, we can go into this direction, and we can actually interactually to add the information and to scan more. So we thought about semantic fusion, something very, very similar to the Mark talk yesterday. So it's the same like Kinect, but instead the simple volumetric information, we will have a semantic information in our memory of our computer. So when the new frame arrives, the RGB and the depth data, we do some semantic segmentation and trying to combine the new semantic information with existing semantic information, and of course the update the model in the memory of computer. So this is how it works. Now, I'm calling this almost semantic fusion because there's no semantics there whatsoever. So it's very, very simple segmentation, but we're adding, so segmentation based on the plane fitting, but we are adding more and more information, at least about the plane segments. So you see, so now the whole wall, it's of the same color, and the table of the same color, and chairs are from similar colors. So how to do a semantic segmentation? Pick your favorite one. Today is popular fully convolutional neural networks. We did something different in 3 stages based on RGBD stream. Detect objects, recognize objects, and then do some foreground, background segmentation. For detection and recognition, we use so-called faster RCNN neural network, which is simultaneously produced object proposals and recognizing the objects. Now we have also the depth stream in addition to RGB. So we converted the depths in so-called HHA representation, horizontal disparity, height above the ground, and angle to gravity. And this is how we did object detection and object recognition. And for foreground, background segmentation, we are using our random forest, but you can use any other algorithm. Now, here the movie slide. So it's work in progress, so I don't have the latest movie. Sorry about this, but we do really believe that a semantic fusion or similar algorithm should be in the basis of scene understanding. And finally, the final 2 slides, that even in registration, so the registration, it's finding the model in the space of the models and fitting it exactly to our scene, to our scanned volumetric data. Even here, we do think that maybe for fine registration, to fit all fine details, we need to wait till we will scan all the room or till we will have enough information. But we can start at least to estimate the rotation and, for example, scale of the object from single frame. So this is what we are doing. We are training convolutional neural networks, which from single frame RGB, HHA, and normals data estimate the orientation and the scale of the object. So conclusions, it's pretty much you understand what I wanted to say. Use semantic information. Now, a little bit more advertisement. We are creating the data set to use our camera. So it's indoor data set with 50 categories and almost 80,000 images. For now, it's only bounding boxes, but we are going to train a segmentational system, so it will be fully segmented. So it will be available for research and for anyone in a few months, and if you are interested, talk to me or talk to my friends. And the final thanks slide, thanks to our team, Perceptual Computing Research. and my teammates, and other teams in perceptual computing, and specifically to Jonathan Abrahamson, who helped me to create these movies. And final slide. We are still hiring, so best and brightest, if you want to join, come to talk to us, and we are looking for you. Thank you.